All right, so looking at titration, and we'll go through simple titration, back titration, and also redox titration. Now, titration itself is a volumetric analysis. So it is used to get to this setup you are seeing here is what we'll be calling as a volumetric analysis that we are going to use to find the unknown concentration. Now there is a substance that we are going to be able to put here and the substance that will remain here. So the substance, of course, we know this thing here is a burette, and then this thing is a conical flask. Right? We also have the stand there and the support system. So we are going to have two reagents. One reagent we are going to put it here, the other reagent we are going to put it in here. So the reagent that we put in the burette is the one mostly that we want to determine, because you are going to know the volume for this compound. One thing that we need to know is that the burette itself has got a fixed volume. So some are going to end at 50 mils, others are going to end at 25 mils. So we are going to transfer that liquid to this burette. So it does read a specific volume. You can use a pipette to fill this thing, or you can simply get that reagent, you start pouring it using a beaker. Now as you are pouring, make sure that your height is at least higher than the height of this thing, because if not, those are some lab hazards. If not, if it gets to pour in your eyes, these chemicals are very much dangerous. Another thing that we need to know that these chemicals that you put in here, you don't smell them. So if you want to know their smell, because some of these reagents you can actually identify them by their smell, so you get to fan. So you get this cup and then just bring your nose a bit of a distance, start using your hand to push the air towards your nose like that. So you are fanning the gas towards your nose. So you don't do it with your nose, because they can be they can cause irritation to your nose, or even like to your respiratory system. Others are very harmful. Another thing is that you mostly want to avoid putting sodium hydroxide, which is a base, in the burette. The reason is sodium hydroxide is able to react with the carbon dioxide in there, forming sodium carbonate, which is a liquid, a solid, and that one is going to be able to block the tap here, and so the liquid will not be able to move into the conical flask. So those are some things that you want to avoid in the lab, right? So we have got the substance that we are going to put in the burette, that is going to be called the titer. The substance that you get to put in the conical flask is called the analyte. Okay, so we have got the titer and the analyte. Now since the titer is in the burette and the burette has got a volume which is known, meaning that the titer has a known volume, right? It has a known volume. And then in the conical flask we can put we are going to put something, of course, which we know the volume, non volume. But most of the times you also find that we also know the concentration, right? So let me first finish with a titer, which we can as well refer to as a titrant, like that. So a titrant is a substance or a reagent where you precisely know the concentration, okay? Non-concentration, because you know the concentration, of course you put it in the burette, you also know the volume. So you know these two things. And because of that, it is referred to as a standard solution. A standard solution is a solution whose concentration and volume is known. Now, in the conical flask, you are putting something of known volume. You know the volume. Also, conical flask can hold a certain volume, maybe up to 25, but you want to determine the concentration. So, unknown concentration most of the times. That's what you want to determine. So, this is a setup of a very simple titration. Now, depending on the reaction that you are talking about, let's say you are talking about hydrochloric acid, that's the one you are using as your titer, and then sodium hydroxide as your titrant. So, the reaction is going to happen between hydrochloric acid and sodium hydroxide. This is an acid-base reaction, which we also this is going to be referred as simple titration or a direct titration. A back titration is also referred to as an indirect titration. So we're going to form sodium chloride and water here. So since we already know for the titer, we already know the concentration and the volume, we know that number of moles is given by concentration times volume. So using this reaction, we can actually determine the number of moles of sodium chloride. So actually, we already know the number of moles of sodium chloride since we know the concentration and the volume. Now, sometimes the volume is going to be given in milliliters. We need to make sure that we are using the volume in liters, or the volume should be in decimeters cubed. The concentration is going to be given in molar or mole per liter. Since a liter is same as a decimeter, so it's also the same as mole per decimeter cubed. Right, so we know the number of moles of hydrochloric acid. So we can actually determine the number of moles of sodium hydroxide. From the balance reaction, we can see that number of moles of hydrochloric acid is equal to number of moles of sodium hydroxide. So if we know the number of moles of sodium hydroxide as being 2 moles, then we already know the number of moles of hydrochloric acid also as being 2 moles, right? Meaning that the number of moles of hydrochloric acid is also going to be 2 moles. How did we find? We multiply the concentration of sodium hydroxide with the volume of sodium hydroxide. So if the question is asking us to determine this unknown unknown concentration, we can now say concentration is number of moles over volume. Since we know already the volume, we'll just substitute here, and we've already determined the number of moles. We'll substitute also there. We are going to find the concentration of the substance that we don't know. So basically a very simple and direct way. This is a direct titration or a simple titration. Now in a case where we have got diprotic acid instead of hydrochloric acid, let's say we are using sulfuric acid, which is a diprotic, meaning that it has got 2 protons. And let's say we are still using the sodium hydroxide. So the reaction that gets to happen here, we're going to have sodium hydroxide with sulfuric acid, and this will still give us a salt and water because it is acid base. What salt are we going to form in this reaction?
Sodium sulfate.
Yes, sodium with a 2 down and then sulfate, because we know that sulfuric acid, a sulfate itself has a valence of 2, which is going to come down the sodium. Sodium has got a valence of 1, which is supposed to come here, but you don't show that. We are also going to form water. Now this reaction is not balanced, so we have to balance it. We are going to put a 2 here. That makes 2 oxygens plus this 4, 6. And then the other side, we're also going to put a 2 there, so now the reaction is balanced. So here again, for the titrant or the titer, sulfuric acid, we know the concentration, we also know the volume, meaning that we basically know the number of moles of sulfuric acid. So we know the number of moles of sulfuric acid. Let's say the number of moles of sulfuric acid is 1 mole. This we can find the number of moles of sodium hydroxide. Number of moles of sodium hydroxide divided by the coefficient, which is 2, is going to be equal to number of moles sulfuric acid divided by the coefficient, which is 1. So meaning that the number of moles of sodium hydroxide is basically going to be 2 multiplied by the number of moles of sulfuric acid, which is 1. So the number of moles of sodium hydroxide is going to be 2 moles. And we can as well determine the concentration of sodium hydroxide. Concentration is number of moles over volume. Since we already know the volume and we've already determined the number of moles, we can basically find the concentration also. So this is basically a simple titration. Now the difference between a simple titration and an indirect titration, which we also refer to as a back titration, is that for a back titration, you mostly work in a back way just from the name back titration. So what you are going to have is you are going to have two reagents, A and B, right? You are going to react reagent A with reagent B to form a certain product, let's say C. Now one of these is the limiting, one of them is an excess reagent. So let's say A is excess, that means that B is going to be limiting, meaning that B is going to be used up completely. So let's say I had put B here, right? And then I put A here. So when I titrate A into B, the whole of B is going to be used up. So we are going to note the volume of A that we have used. We are also noting the concentration of A, right? We are noting the concentration of A and the volume of A. Now, since A, not just A, but also B, since everything is known, for us to know which one is limited and which one is in excess, it means we know the number of moles for both of them. So what is going to happen is, since A is in excess, when you get to react this, after, so you basically, what you do is you basically measure a volume here. You don't do like in the previous one. Let me just mention it. On the previous type of titration, which is a simple titration, you are going to be careful by opening the tap. So you are going to be opening the tap carefully because you have got a reagent here. So you are opening the tap carefully. When you start seeing the color changing here, so you open a bit. When you see the color changing, immediately the color changes depending on the type of indicator that you are using. Immediately the color changes, you are going to close the tap. Now, the point at which the color changes when you add this titrant to the analyte, that point is going to be called the end point. What is the end point? The point at which the color actually changes, the color of the what? Of the indicator. Because when you had put B here, you also added an indicator, for example, methyl, orange, or phenolphthalein. And then another thing that you are going to do here is that, of course, you have the end point when the color changes. But there's also a point when you have just added enough titrant to the analyte. That point when you have just added enough titrant to the analyte is called the equivalent point. The other name is stoichiometric point. So the stoichiometric point or the equivalent point is the point when you've just added enough titrant to the analyte. But the end point is a point when the color actually changes of the solution. You are able to differentiate those two?
Yes.
Okay. So you also need to take note of the color changes of some indicators, because I've seen some questions being asked like that. So maybe just some which should take interest of, which they must get to bring. We have got bromothimo blue. We also have a litmus paper. This one is common, even from high school we've known this. We have got methyl orange. We also have phenolphthalein. I think we can talk about this. So what will be their colors in the acid and in a base? Let me have an acid here and a base here. So starting with the bromothimo blue in acids. So we have got different acids here. We have got strong acids, weak acids, and such a thing. But I'm just going to talk about them specifically as acids. So starting with the let me start with the phenolphthalein. In acids, phenolphthalein is colorless. So that means that when you are using phenolphthalein as the indicator, the acid should be in the what? In the conical flask, because you add the acid, you whatsoever you are going to add here, you are going to add them together with the indicator. So that by the time you start pouring the base inside, the base, the color of phenolphthalein in a base is pink. So it, whenever you start seeing a pink change as you are putting the base from the burette, you should know that you are reaching the what? The end point when the color changes. And the end point is mostly the same as the equivalent point. Now when you are using methyl orange in acids, it is pink. That is for methyl orange. And then it is yellow when it comes to bases. And then a litmus paper, of course, uh, we know we have got a blue litmus paper and a red litmus paper, but for acids, the litmus paper is going to be red, right? So that means that when you use a red litmus paper, it will not change color, and then in bases, it's going to be blue. So these are some things that you are able to see, right? And then when you are using the bromothermo blue, the colors are going to vary. When you have got a very acidic solution, like something that is very acidic, meaning that the pH is from like 1 up to 4, you are going to see a yellow color, right? And then at neutral pH, bromothermo blue is green, and then in a base, the color is blue. So these are the colors that you're able to see for these. For methyl orange, some questions will come. What will be the color changes when you start titrating? So in very strong acids, for methyl orange, in very strong acids, the color is red. As the acid reduces concentration, the color is orange and then yellow. It is also yellow in a base, meaning that when you are using this methyl orange, you are going to use a base here so that you add it together, because in a base is going to be yellow. So as you start adding the acid, it will change from yellow to orange, and then from orange to red when you have exceeded, like you have added too much acid. So that is the process that is going to happen on this one. So basically that is it. That is a simple titration. So we also need to take note of those color changes. Now when you're talking about a back titration, as we were saying, a back titration, you are going to have A and B reacting to form some certain product C. So if you've put A in the burette, basically what you do is mostly the first one, you have got something that is in excess. You know that A is in excess, right? And then you know that B is limiting. So the first thing that you do is you are not even interested in putting these for the first part in the burette. All you do is you are just going to mix. You just get this A in a beaker, B also in a beaker. You mix them. You pour them all in the what? In the conical flask. You already know that one is in excess, one is limiting. Of course, you cannot be told like that, but you are going to be given the concentration and the volume, also the concentration and the volume, or something like that, so that you are able to determine the number of moles and determine which one is the limiting reagent. Now, when that happens, this one which is in excess, when the reaction is complete, some of it will still remain unreacted. Okay? So that part of A that has remained unreacted, you are going to react it with another compound D, and you are going to form some E. Now in this second reaction, this is a complete reaction, meaning that the O of A and the O of D have reacted. Nothing has remained. Okay, so what you are going to do in this reaction is that you are going to be given data about this one most of the times. You are given data about this one, so you know the number of moles of D. It can be indirect. It's not like you directly know the number of moles. It can be indirect, meaning that you can be given the concentration and the volume of this one, meaning that you can determine the number of moles from concentration times volume. Using balanced equation, you say number of moles of this over the coefficient is equal to number of moles of this over the coefficient. So you can as well determine the number of moles of A, right? So you know now the number of moles of A which have reacted with D. Now at the beginning of the reaction, remember you also knew the number of moles of A, though it was in excess. So you are going to determine also the number of moles of A which are what? In excess. So these ones are in excess. Everything which remained reacted in the second reaction. So you can determine actually how many moles reacted with B in the first reaction. So number of moles of A that reacted in the first reaction is going to be equal to number of moles of A which is in excess minus the number of moles of A which reacted in the second reaction here. So that will give you the number of moles which reacted in the first reaction with B. So if you know the number of moles of A that reacted in the first reaction, you can now determine how much of B reacted. So that is how you are able to determine how much of the limiting reagent reacted using a back titration. Now, a redox titration is more the same as a simple titration, except the way I showed, like using an indicator. You don't use an indicator for a redox titration because what you are using are redox reactions. And for redox reactions, each ion has got its own color. Ion 2 plus, when it gets to change to ion 3 plus, you are going to be able to determine. For example, if ion 2 plus is red and then ion 3 plus is blue. So if the reaction happens, you see the color changing from red to blue, just know that this one has been formed. So for a redox titration, you don't use any indicator. What determines that you've reached the end point is the color change of the ions. Is this okay?
Yeah.
Okay, let's consider some exam practice questions. So the first question we have, a 1 gram sample of potassium carbonate which has got a molar mass of 138.2055 grams per mole is dissolved in enough water to make 250 ml of solution. A 25 milliliter aliquent, so aliquent is simply a portion, is taken and titrated with 0.1 molar hydrochloric acid. And then this is the reaction that gets to happen in the second phase. How many milliliters of hydrochloric acid are used? How many milliliters of hydrochloric acid are used? Now, we should be able to interpret the data. So we're supposed to have two reactions here. Okay, so, and now for this one, even if it's more a back titration, we don't have two reactions. So it's a special one. So what we have is a 1 gram sample of potassium carbonate. All right. So since we already know the molar mass and we know the mass of potassium carbonate, we can determine the number of moles direct from here. So the number of moles of this potassium carbonate is given by number mass over molar mass. So this will be the mass, which is 1, the molar mass, which is 138.2505. If you have a calculator, you can get to punch that. So 1 divided by 138.2055, this is going to give us about 0.00723560 moles. You need to make sure that you use a lot of significant figures. Don't round off yet. Now, we've been told that this compound is dissolved in enough water to make what? To make 250 ml solution. So when you get to dissolve number of moles in water, you are going to be able to determine the concentration. How do you find the concentration?
Moles over volume.
Yes. So concentration will be number of moles over volume. The number of moles we've already determined that 0.00723560 moles over volume. Now the volume, we need to make sure that we are using in liters. This one is in milliliters, so simply multiply by 10 to the power negative 3 to convert to liters, or divide by 1000. So the answer that we have, which is a 0.007, divide that by 250 times 10 to the power negative 3. So the answer that we get as the number, as the concentration, is 0.02894240823. This is molar, which is mole per liter. So this is the concentration. Now look, from this concentration, we just pick a portion that is an aliquot. Okay, so a 25 mils aliquot, so you have picked only what? A portion, right? You've only picked a portion. So this portion that you have picked, what will be the concentration of this portion that you've picked? Because the whole solution that you had made had a volume of 250, but you have only picked 25. So if 250 has got this concentration, what of 25? What will be the concentration, right? So we can be able to determine. Actually, the concentration is the same. Sorry. So I want to determine the number of moles. Like this same solution that you have, you pick now this aliquent. You pick this portion. It is the same concentration. You can think of this. You get water, you add sugar, and then that solution that you've gotten, they say you just pour some in another a different cup. So that collection you've gotten from a different cup is the same concentration as the one from where you poured. All right, what will just be different is the number of moles, because in the cup, the original cup, there were a lot of particles in comparison to the cup where you've just poured some. So we should be able to determine the number of moles which are present in 25 mils. So say number of moles of potassium carbonate in 25 mils is going to be what? Concentration times volume. What is the concentration? That is 0.028. Okay, 0.0289424, and then multiply by the volume. The volume we want to find in 25 mils. Now remember 25, we will say at 25, this is mils we want to convert to liters, so times 10 to the power negative 3, like that. So multiply by 25 times 10 to the power negative 3. So the number of moles that we are going to determine is now 0.00072356021 moles. Are we moving together?
Yes.
Okay. Can now remove this. Now, this same portion, this adequate that you've picked, you titrate it with zero point 0.1 molar hydrochloric acid according to the equation. Potassium carbonate react with 2 moles of hydrochloric acid. Even if they've not given you a balanced equation, make sure that you write a balanced equation. I'm not interested in the product. What I'm interested in is the potassium carbonate. We already know the moles, okay, which are these down here. And then the hydrochloric acid, we know the concentration, right? We know 0.1 molar. That is all we know. Now I want how many milliliters of hydrochloric acid are we going to use to react with these moles? So from the balance reaction, we can say that number of moles of potassium carbonate is going to be equal to number of moles of hydrochloric acid over 2. Meaning that the number of moles of hydrochloric acid is going to be 2 times the number of moles of potassium carbonate, which is 0.00072356. We'll complete the numbers. So the number of moles of hydrochloric acid is going to give us, so just multiply that value by 2. That is going to be 0.00144712041 moles. Now remember, we used a molarity of hydrochloric acid of zero point 0.1. Now I want to find the volume. How do you do that? What is the relationship we are going to use? What do you think?
We can use moles over concentration.
Okay, so we know that number of moles is concentration multiplied by volume. So the number of moles we've already found, 0.0014471. That will be equal to concentration, which is zero point 0.1 times volume. So simply divide both sides by zero point 0.1. So therefore the volume is going to be the answer that we have divided by zero point 0.1. That is going to be 0.0144712. This is going to be in liters. Okay, in liters. But the question is saying find how many milliliters. Remember, when you are moving from milliliters to liters, we are multiplying by 10 to the power negative 3. So to move from liters to milliliters, multiply by 10 to the power positive 3. Okay, so simply multiply this value by 1000. So the volume you are going to find is going to be 14.47 milliliters. This is the volume of hydrochloric acid that is going to be used. We are good?
Yes.
Let's also consider this one. A 1.25 gram sample of limestone was added to 50 mils of zero point 0.1 millimeters of hydrochloric acid. Do you know what limestone is? What is limestone?
Limestone.
Mhm.
Not really.
It's calcium carbonate. So here, this calcium carbonate is impure. Since they've just told us it's a sample, so it's impure. So calcium carbonate was added to hydrochloric acid. So we need to find out a balanced reaction that happens. Okay, this is going to form calcium chloride and carbon dioxide and water. Like every time you react an acid with a carbonate, you always form a salt, carbon dioxide, and water. So we need to balance this reaction. We need to put a 2 here, right? I think it's now balanced. It's now balanced. So this is the first thing that happens. But from the data we've been told is that we used 1.25 grams of limestone, and this was added to 50 mils of hydrochloric acid. Not just 50 mils, but 50 mils of 1 molar hydrochloric acid. Right? So this is the data that we have. Now, when the reaction stopped, the solution was made up to 250 milliliters with distilled water. In other words, it was diluted. All right, we added water to dilute the solution. So we diluted the solution, and then from that diluted volume, we got what? We got 25 milliliters. We only got a sample of 25, which was pipetted into a conical flask and was treated. In other words, it was now reacted with a zero point 0.1 molar sodium hydroxide in the presence of methyl orange indicator. Now, it required exactly 30 milliliters. So this 30 milliliters is the sodium hydroxide that we are using, right? Now determine the percent calcium carbonate in the sample. This is a back titration, remember. One of these is supposed to be the excess reagent. And from what you've been told, you want to determine the percentage calcium carbonate in the sample. Definitely, this should tell you that calcium carbonate is in excess. Okay, it is in excess. So, if calcium carbonate is in excess, meaning that some of it is going to remain. Actually, that sample which we picked to react in the second reaction was just calcium carbonate, which reacted now with the sodium hydroxide. And this reaction is going to form, uh, what are we even going to form here? Sodium carbonate. Let me see if I'm not even picked a wrong thing. Okay, limestone. Okay, reacting calcium carbonate. Now, calcium carbonate itself acts as a base, and we are reacting that with sodium hydroxide. Okay, let me take it stepwise because we might be in a wrong path here. Okay, so when reaction stopped, the solution was made up to 250. I'm going to work with it stepwise, starting first with the first data instead of me going to the next. So let me first determine the number of moles of hydrochloric acid which reacted here at the beginning. So number of moles of hydrochloric acid initial. These are the initial moles. So these will not be necessarily those which are going to react with calcium carbonate because calcium carbonate is in excess, right? So number of moles of hydrochloric acid which was present initially is concentration times volume. So the concentration here is 1, the volume is 50 milliliters. But remember, we need to convert to liters because concentration is in molar. Molar is more per liter, so it can't cancel with the milliliters. So multiply by 10 to the power negative 3. So that is just basically 50 divided by 1000. And that is going to give us 0.05 moles of hydrochloric acid. These are the moles which were present initially. Now, I'll not go to this statement, when reaction stopped, solution was made up to what? A solution was made up of to 250 moles. Actually, in this reaction, calcium carbonate will not be what we are going to use. We are going to use hydrochloric acid as the one, like the hydrochloric acid is the one which is going to proceed to react with the sodium hydroxide. The calcium carbonate can't react with the calcium carbonate in this reaction. Both of them, they more act like bases like that. So what we are going to have, this is telling us that it's the hydrochloric acid which was in excess. This should be an error that I have to be correct to correct. So the hydrochloric acid was in excess. This is going to react with the sodium hydroxide at the end. Okay, and this is going to give us sodium chloride and water. From the balance reaction, 1 mole of sodium chloride reacts with 1 mole of hydrochloric acid from the balance reaction. Now, I've been told that when the reaction was happening, what happened? 0.1 molar of sodium hydroxide was used. So 0.1 molar of sodium hydroxide was used. And we've been told it required 30 moles. So what 30 moles? Of the same sodium hydroxide, it requires 30 moles. Remember, you already know about hydrochloric acid. You already know the volume that you use because it was in excess. You already know that's the 25 that you got. So definitely this 30 can't be for this hydrochloric acid because you already know that 30 moles. So let's determine the number of moles of sodium hydroxide. Now from this reaction we can see that number of moles of hydrochloric acid is the same as number of moles of sodium hydroxide because their mole ratio is 1 to 1, and that would be concentration times volume. Concentration is 0.1, the volume is 30 milliliters, so convert that to liters, so multiply by 10 to the power negative 3. So 0.1 times the 30 divided by 1000 or multiplied by 10 to the power negative 3. This gives us 0.003 moles of hydrochloric acid, which reacted in the first reaction. Let me pause a bit here. Are we good?
Yes.
Okay. And then so this is why it is called back titration, because you are going to be working backward. Like you start with the second reaction, you are going now to the first reaction. So these are the moles of hydrochloric acid which reacted in the second reaction. Now we need to go from these moles. We find what moles reacted in the first reaction, because of course these are the moles which were present initially, but they all didn't react. Like this is what was present. So we need to find what reacted with what? Calcium carbonate, because for the calcium carbonate everything reacted, right? So what moles of hydrochloric acid reacted? Now remember, it is from a 1.25 milliliters which reacted with the sodium hydroxide. What does this tell us? We can actually determine the concentration of hydrochloric acid which reacted with sodium hydroxide, and that is given by number of moles over volume. Number of moles is 0.003, the volume is 25, but convert this to liters times 10 to the power negative 3. 0.03 divided by 25 times 10 to the power negative 3. That has given me 0.12 molar. Okay, that is the concentration of hydrochloric acid. Now remember, this 25 milliliters, you had picked it, all right? You only got it from 250 mils. So the whole concentration was 250, but you only got a 25 milliliter sample, meaning that we should be able to determine how many moles were present in the 250 mils where we got this 25 mils. And what do you think? How are we going to be able to find that?
We will look at video. We can divide this 25 into the initial multiplied by the moles that we got.
Okay. So what we basically do is Number of moles, actually this one I've found is concentration. Number of moles is equal to concentration times volume. Okay, number of moles is concentration times volume. The concentration is what we've determined down here, 0.12. Multiply by the volume. The volume now where we got is 250. So that is going to be 250. That is in mils. So multiply by 10 to the power negative 3. Okay. So times 250 multiplied by 10 to the power negative 3. So then that is going to give us number of moles being 0.03 moles of hydrochloric acid. So these are the moles of hydrochloric acid which we had gotten, right? Remember initially we had 0.05 moles of hydrochloric acid, but these are the moles of hydrochloric acid which we had gotten from this 0.05 and reacted with the sodium hydroxide. So we can determine the number of moles of hydrochloric acid which reacted with calcium carbonate, and that would be basically the number of moles of hydrochloric acid present initially minus those which reacted with the sodium hydroxide. Therefore, those which reacted with the sodium carbonate is 0.02 moles. We are good?
Yes.
From these 0.02 moles which reacted, we can now determine how much calcium carbonate they reacted with. How much calcium carbonate they reacted with, because these are the ones which reacted with calcium carbonate 0.02. From the balance reaction, we can see number of moles of calcium carbonate over 1 is equal to number of moles of hydrochloric acid over 2. So the number of moles of calcium carbonate which reacted is going to be 0.02 divided by 2, because these are the ones which reacted. So that will give us number of moles of calcium carbonate to have reacted as 0.01 moles. Now we need to convert this to mass. We need to find the mass of calcium carbonate which actually reacted, right? Which actually reacted. So the number of moles, sorry, not the number of moles, but mass of calcium carbonate which reacted is number of moles times molar mass. What is the molar mass for calcium carbonate? 0.01. That should be 100.01. We can use 100. So the mass we are going to find is 1 gram. So this is why I was confusing to say this one was in excess. So it is not just any, it's of course a back titration, but even if not everything here reacted, it doesn't mean that it was in excess. It's just that it was in, some portion was impure, so only the pure form reacted. That's why at the beginning I said calcium carbonate was in excess. The one which was in excess is this one, but this one there was some impurity, so not the whole of 1.2 could react. That is why I want to determine the percentage calcium carbonate in the sample. So that basically what we want to find is the percentage purity. Okay, that's the percentage calcium carbonate which reacted. So that would be the mass of calcium carbonate which reacted divided by the whole sample, which is 1.25, and then multiply by 100%. So 1 divided by 1.25 multiply by 100. So that is giving me 80%. So meaning that the percentage purity for this limestone was 80%. 80% was limestone, and then the 20% was some other impurities. We are good?
Yes.
Okay, so these are two examples we could have done on back titration. Let's also do two examples on redox titration, and then we'll be through. A curious chemistry student analyzed a 10 milliliter sample of solution D to determine the concentration of ion 2 plus ions. Okay, so this student got 10 mils of solution D. So what did he do? He titrated acidified solution with a standard potassium permanganate solution. Remember, the potassium permanganate is standard. Now, this is a redox titration, There are some ions which are spectator ions which are cancelled in the reaction. That is why from this reaction you'll not be able to see some elements or some atoms. So the balanced reaction we have is 5 ion 2 plus plus a manganate ion and then plus 8 hydrogen ions. This one they've already given us a balanced redox reaction. So for a redox titration, make sure that the redox reaction is balanced. Plus manganese 2 plus and then plus 4 water molecules. Now we've been told that the potassium permanganate is standard. So from the potassium permanganate, this is where we've seen the manganate ion. The potassium was a spectator ion, so it cancelled, right? So this is what we have. Remember, this is standard. This ion is standard. But one thing we know is that 10 mils of full solution D, which contained iron 2 plus, was used. So we used 10 mils of this. And then 10 mils of solution was titrated against potassium permanganate solution of concentration. The concentration was 0.02 mole per liter. Volume of potassium permanganate used for complete reaction was 37.5 milliliters. Calculate the first one, oxidation state of manganese in potassium permanganate. The oxidation state of manganese in this compound. So we'll start. The oxidation state for manganese plus we have got 4 oxygens and each oxygen the oxidation state is -2 should give us the total oxidation number which is a -1. So the oxidation state for manganese is going to be 4 times -2 is 8. We take it the other side is going to be +8. +8 minus 1, that will give us +7. So that is the oxidation number for manganese. And then for B, the number of moles of permanganate ions used. Number of moles of permanganate ions used. We can see already number of moles is concentration times volume. So the concentration given 0.02 mole per liter times the volume given is 37.5 milliliters, but the milliliter can't cancel with the liter. That's why we need to convert this to liters by just multiplying by 10 to the power -3. Or we can just say we put a milliliter down, a liter on top. We know that 1 liter has got 10 to the power 3 milliliters. That's why we say multiply by 10 to the power -3, because this will go on top, the power becomes negative. So mils cancel, liter and the liter will cancel. So therefore we're going to have 0.02 multiplied by 37.5. The answer that we have, we divide that by 1000. So the number of moles of permanganate ions is 0.00075 moles. These are the moles which reacted. And then part C, number of moles of iron 2 ions in 10 milliliters. Number of moles of iron 2 ions present in 10 milliliters. It's very direct. Number of moles of iron 2 ion divided by the coefficient, which is 5, should be equal to the number of moles of the manganate ions divided by the coefficient, which is 1. So I mean that the number of moles of iron 2 plus is going to be just 5 multiplied by the number of moles of the manganate, which is 0.075. And that will give us 0.00375 moles. As direct as that, we are good.
Yes.
So you can actually determine the concentration which was used. Also concentration is number of moles times volume. You know the volume is that. Okay, the last example here, a 0.4 gram sample containing manganese oxide without molar mass was reduced by reacting it with 100 mils of 0.1 molar ferrous sulfate in an acidic medium according to the equation. So here is the equation, and thank goodness a balanced equation already. The excess ferrous sulfate, so the sulfate was also a spectator ion, so that's why we can only see iron 2 plus. and don't see the sulfate. So the iron 2 plus is actually coming from the iron sulfate or the ferrous sulfate. So the excess ferrous sulfate was back titrated with 82 mils of 0.023 molar potassium dichromate in an acidic medium as shown by this reaction. Calculate the percentage manganese oxide in the sample. Percentage manganese oxide in the sample. So this question is a combination of back titration and redox titration. Now the only thing is this, redox titration is very simple, but the questions tend to be longer. So students get to be confused, not because the question is hard, but because you feel lazy interpreting the long question, but it's very simple. So from what we have been, the data that we've been given, since this is a redox titration, we have the excess ferrous sulfate, which is the ion, was that back titrated with 32. Okay, we have got 32 milliliters of what? 0.023 molar potassium dichromate. This is where we are having the chromium ions from the potassium dichromate. All right. So from this, of course, there was no dilution in this reaction whatsoever. So we can determine the number of moles of potassium dichromate which reacted. And that would be number of moles of the potassium dichromate ion, which is going to be concentration times volume. And the concentration here is 0.023 molar, which is mole per liter, multiplied by the volume, which is 32 milliliters, but multiply that by 10 to the power negative 3 so that it will be converted to liters. So I've got 0.023 multiplied by 32 divided by 1000. 0.023 times 2 over 1000, that will give us 0.000736 moles. Now another thing is, remember the ferrous sulfate was in excess. Okay, it was in excess, meaning that everything that remained is what reacted here. So number of moles of iron 2 plus which remained to react divided by the coefficient, which is 6, is going to be number of moles of the dichromate divided by the coefficient, which is 1. Mean that the number of moles of the iron 2 plus is going to be 6 times 0.000736. So that will give us 0.004416 moles. Are we good so far? Okay. So these are the moles of iron which reacted in the second reaction. Now I'm going to get back to the first reaction. Remember in the first reaction what happened? Uh, the sample of manganese oxide was reacted with 100 mils of 0.1 molar ferrous oxide. This is the initial, so we can determine the number of moles of iron 2 plus initially, all right, initially. And that is given by concentration times volume. The concentration is 0.1 times the volume, which is 100 mils. So multiply that by 10 to the power negative 3 to convert also to milliliters. So that should give us a 1. Punch that again, 0.1 times 100 divided by 1000. Okay, that is going to give us 0.01 moles of iron 2 plus which are present initially. So we have got the initial moles, we have got the moles which reacted in the first reaction. How can you find the moles which reacted now? I mean, we have got the initial moles and then we have got the moles which reacted in the second reaction. How can we determine the number of moles of iron 2 plus which reacted in the first reaction?
It was initial minus the excess.
Yes, so that would be the 0.01 minus those which reacted in the second reaction, 0.0044 So that will be 0.01 minus 0.004416, and that will give us 0.005584 moles. And then we should be able to determine from the balanced phase reaction how much of manganese oxide reacted. So the number of moles of manganese oxide is going to be equal to the number of moles of iron 2 plus over the coefficient, which is 2. So meaning that 0.005584 divided by 2 will give us the number of moles of manganese oxide, and that is 0.002792 moles. Now we can determine the mass of manganese oxide which reacted with the manganese oxide. Mass of the manganese oxide is going to be number of moles times molar mass. So the number of moles is 0.002792. The molar mass we've already been given there, which is 86.94. And that is going to give us 0.24273648 grams. Now we determine the percentage manganese oxide. How can we do that?
It's the calculated over the sample 1000.
Okay, so the calculated percentage, the calculated mass of manganese oxide 0.242736 over the actual one which was present in the sample, is 0.4 multiplied by 100%. So the percentage of manganese oxide in these samples is 60.68%.